Thank you, Mr. Chairman. Thank you for your kind introduction. It's a really great honor for me to have the opportunity to share my research with you. And good morning, everyone. My name is Wen-Jun. I'm from Southeast University in Nanjing, China. Today, I want to show you my research is flexible passive wireless pressure and moisture sensor for wound monitoring. Wait a moment. And my presentation will include these 4 parts: background, introduction, design and simulation, fabrication and experiments, and finally, some conclusions will be given. First of all, let's see the background of my introduction. As we know, that wound management relates to millions of patients' health, while wound healing is such a complicated process involving a series of biological events which can be affected by many different factors, including pressure, temperature, and moisture. A controlled and appropriate pressure and moisture can help to accelerate the wound healing, while abnormal pressure and moisture will often cause pain to the patient and interfere with the healing process. So in order to monitor the pressure and moisture level on the wound site, researchers have proposed many different kinds of sensors, but most of them required a wired connection, which will limit the patient's mobility and interfere with their daily lives. Some others have proposed some wireless sensor system that are much better, but still they need a battery and a complex circuit which couldn't be bendable, so the patients often feel uncomfortable. So we think a more attractive solution should be wireless and passive and totally flexible, with no battery, no any inflexible elements, which can make the patient feel more comfortable. This is why we try to use the LC sensor to solve this problem. This is a typical structure of the LC sensor system. It is composed of a readout coil and the sensor chip. There's a magnetic coupling between the readout coil and the sensor chip, so the resonant frequency of the sensor can be wirelessly read out through the readout coil. This kind of technology has many good features. It is wireless, it is passive, and since there is no battery in the sensor chip, so it can have a long lifetime. And since the structure is very simple, it can be designed as totally flexible. So all these features make it a perfect solution for wound management. Now let's see our design and simulations. The biggest challenge to realize a 2-parameter monitoring is that the interfere of the different LC sensors. If we just put 2 LC sensors together like this, there will be a magnetic coupling between these 2 inductors, so the resonant frequencies will be deviation, making the measurement result unreliable. In order to solve this problem, here we designed a new kind of dual resonant circuit, which is composed of 2 equal inductors and the 2 symmetrical sensing capacitors C1 and C2 in response to one tested parameter, and another sensitive capacitor C0 to the second parameters of interest. Using the Kirchhoff's law, we can get these formulas, and where the Qing-An is the charge distribution of the circuit loops. So these 2 resonant frequencies of the circuit can be driven. As you can see, F2 is only related to Y, so and when X is much higher than Y, then F1 depends mostly on X. So these 2 resonant frequencies can be considered as mutually independent to each other, which make it possible to realize 2 parameters monitoring. And in order to verify our theory, we make a simulation through the advanced design system. As you can see, the resonant frequencies of the circuit can be detected through the input return loss measurements. And the simulation results agree well with the theoretical calculations. As you can see, when Y is fixed as 1 picofarad and X is increased from 10 to 12, then F1 is decreased while F2 remains stable. And when X is fixed as 10 picofarad and Y is changed, then F2 is decreased while F1 is relatively stable. Here, based on the circuit, here we designed a smart bandage, which is composed of a dual parameter sensor enclosed by a commercial bandage, and this is the structure of the sensor. As you can see, C0 is an interdigital capacitor with graphene oxide as the moisture sensing material, and the C1 and C2 are two symmetrical plate capacitors in response to pressure, and the microstructured PDMS layer is utilized as the dielectric. And according to the equivalent circuit, here we can see that F1 is dependent on X, so it should be moisture sensitive, and F2 should be pressure sensitive. Now let's see the fabrication and experiments. The first step is to make a microstructured PDMS. It is fabricated through a silicon mold with arrays of inverted micropyramid as the mold. And the second one is to make the sensor circuit, which is fabricated by electroplating process on the polyimide substrate. Here is the photograph of the fabricated sensor. And the resonant frequencies can be detected through a read dot coil connected with a network analyzer. And here you can see there are two obvious resonance peaks can be observed from the minimum of the input return loss. And the first one should be moisture sensitive, and the second one should be pressure sensitive. Now, in order to test the moisture response of the sensor, here we use a humidity test chamber, inside which the gas pressure can be considered as stable. And the result shows that when the relative humidity is increased from 20 to 80, then F1 gives a sensitivity of 61 kHz per percent, while F2 is nearly stable. And this is the pressure response test setup. A sealed chamber is utilized to control the gas pressure inside the chamber, while the relative humidity is stable. And this is the result. It shows that when the pressure is increased from 0 to 100 mm of mercury, F2 gives a sensitivity of 388.6 kHz per millimeter of mercury, while F1 is relatively stable. And finally, I want to make a summary of my presentation. Based on the normal LC-type dual resonance circuit, we design a flexible passive wireless pressure and moisture parameter sensor for wound monitoring. And the experiment shows that these two resonant frequencies are in response to moisture and pressure respectively, and gives a very good sensitivity. And the total sensor is wireless, flexible, and no battery or any inflexible elements in the sensor. So we think it should be a perfect solution for wound management. And thank you for your attention. Thank you.